Sairam, and welcome to the next session in computational linear algebra. After having a brief idea about what are eigenvectors and the procedure to calculate them, let us talk about the more important question: why are we dealing with eigenvectors? Let us start this session with a prayer. Om Saishwaraya Vidmahe Satyadevaya Dhimahi Tanna Sarva Prachodayat. Om Shanti Shanti Shanti. Let us ask this very important question: why are we working, or why are we striving hard in order to find eigenvectors of a given matrix or a transformation? The first reason that we are going to state is that eigenvectors can help us diagonalize a matrix. We are not actually answering the question why even diagonalize the matrix and what is diagonalization, and what is the use of it. We will definitely take a look at those questions as well towards the later half of this session. But the first reason that we want to state is that we can use eigenvectors and we will be able to diagonalize a matrix. Okay, let's take a look at this very important statement and understand what is diagonalization and also understand how to diagonalize a matrix. Suppose I have a square matrix, and if it has n independent eigenvectors, that's a very, very important statement we are making. If it's a square matrix, and if it has n independent eigenvectors, then we can use them in order to diagonalize this matrix A. How are we going to do it? Let us take a matrix called S, where we place all the eigenvectors as columns, right? So let S be a matrix where these eigenvectors are kept as columns. Okay, then this is the claim. The claim says that S inverse times A times S is going to give me lambda. So this is the first time we are looking at this kind of an alphabet. So we are going to call this as the capital lambda, and what it stands for is a simple diagonal matrix with all the eigenvalues on the diagonal. That's it, right? Rest of them are all zeros. It's a simple diagonal matrix, and therefore we want to check whether this fact is true or not. And with this claim being proven, let us see if that will be beneficial for us. Okay, so let's place into the matrix S all the eigenvectors x1 to xn, and let us look at A times the matrix S. A times S is going to look like this, and let's look at the columns of the product matrix. Each one by the column view of multiplication, we can easily write it as first column being AX1, second column being AX2, etc. till AXN. What do we know about x1 to xn? They are all eigenvectors, and therefore it tells us that AX1 is going to be same as lambda times x1, or lambda 1 x1. Similarly, when we talk about AX2, it's another eigenvector. Therefore, we can call it as lambda 2 x2, right? Because we have taken lambda 1 to lambda n to be the eigenvalues of A. So let's replace them with the product, which is a scalar times the vector lambda 1 times x1, lambda 2 times x2, so on up to lambda n times xn. When we look at this from the column view of multiplication, this can be written as all the x1s to xn as in a vector form. Put that matrix ahead, followed by either we can put a single column of the lambdas, or we can put it as a diagonal matrix where the lambdas are across present in this diagonal, right? Rest of them are all zeros, right? You can take a look at the column view of multiplication, and we will be able to obtain this product. And what does that give? This is nothing but S, and this is nothing but lambda, which we said is the capital lambda, right? And what have we done? We have got AS is equal to S times lambda. All right, and therefore from here we will be able to figure out whether we can apply a S inverse on both sides, and therefore we can get S inverse times AS to be lambda. But for S to have an inverse, we must be sure that it has got n pivots. Here comes the important fact. Since we have assumed that the columns of the eigenvectors are linearly independent, that is why we were initially itself we were saying that it's a very important fact that we are assuming. So if that is the assumption, then it means that S will have n pivots, and therefore I can get the inverse. So let's apply the inverse on this, and that's it. We got our equation which says S inverse times AS is equal to capital lambda. Okay, so what? I mean, what's the big benefit of it? We really don't know at this point, but let's just proceed and understand a few things before we get into applying this concept. Now, we said we are making a major assumption of the eigenvectors being linearly independent. Let us talk about the condition when will the eigenvectors be linearly independent. Let's take a look at that condition. So here is the next fact or the next statement. It says if the eigenvectors of a matrix correspond to different, right? So the keyword here is the different or distinct eigenvalues, which means that the lambda 1s to lambda n's, none of them are same, right? All of them are all different from each other. Then the eigenvectors are linearly independent. We will try and prove this statement, but before we prove, we should not take the opposite to drive a wrong information. It doesn't say that if the lambdas are same, then the eigenvectors will be dependent. No, that statement can't be inferred from this statement. All that we are saying here is that the eigenvectors will be independent if at all the lambdas are distinct. So when I find that my eigenvalues are distinct, there is a guarantee that my eigenvectors are independent. But when the lambdas are not distinct, I really cannot say about my eigenvectors. They could be independent or they could be dependent, right? So let us look at this statement and try to prove this current fact. We are going to use the induction principle here. So let me start off with a simple n equal to 2. If let's say that I just have a 2 by 2 matrix, and we have the eigenvectors for it and we have some eigenvalues for it. So I am going to assume that x1 and x2 are the eigenvectors for this matrix A, which is 2 by 2, and lambda 1 and lambda 2, only two of them, two eigenvalues, and I am assuming that they are distinct, two different eigenvalues corresponding to their eigenvectors, which are x1 and x2. Let me take two simple constants such that c1 times x1 plus c2 times x2 goes to 0. Now remember, we want to prove that x1 and x2 are linearly independent, and look at the way that we are already attacking the problem. We are going with the definition of linear independence, as simple as that. Now in this equation, if we are at the end able to prove that c1 and c2 are only zeros, then we have done it, right? Then it means that x1 and x2 are linearly independent. Alright, so let us assume that this is true for some constant c1 and c2. Let me now pre-multiply this on both sides by a. Okay, so if I multiply here, this I know the right side will remain 0, there is no problem. Now look at c1 times ax1 and c2 times ax2. They are eigenvectors. Therefore ax1 would become lambda 1 x1, ax2 will become lambda 2 x2. Therefore this equation changes to this equation, multiplication by a gives me equation 2, and what I have now is c1 lambda 1 x1 plus c2 lambda 2 x2 is equal to 0. That gives me an idea. Looking at these two equations, actually I can eliminate this part of it, right? So I'm going to, from the second equation, subtract the first equation with the multiplying it by lambda 2. So let me multiply this entire equation by lambda 2 and subtract from the equation 2. So these two terms will get cancelled. I would have only this part, and here is what we have: c1 times lambda 1 minus lambda 2, this expression, times x1 equal to 0. Look at the interesting part in this equation. We know that x1 is an eigenvector, and we are interested only in eigenvectors which are non-zero eigenvectors, and therefore this is a non-zero eigenvector, right? Now look at the fact that we assumed. We said that lambda 1 and lambda 2 are different, and therefore this obviously this difference can't be 0, that is guaranteed. So look at this. Now I have a non-zero scalar multiplying a non-zero vector. How could it ever produce a 0? It's just a multiple of this vector. It can't produce a 0 vector on the right hand side. and therefore what do we have? This C1 must go to 0. That is the way we are going to look at, and therefore we are getting C1 equal to 0. In a similar idea, we can also prove that C2 is equal to 0. Instead of eliminating this term, we can eliminate the C1 lambda 1 x1 term, and with the same logic we can get that C2 is equal to 0. Very good. So that means that we have the proof that x1 and x2 are independent whenever their corresponding eigenvalues are different. Great. But does that work only for n equal to 2? Can we try for n equal to 3? So it's a very similar concept with respect to n equal to 3. Let me assume 3 constants such that this combination goes to 0, and we are interested in proving that each of those constants must be individually becoming 0. Same idea, multiply by a on both sides. I get C1 lambda 1 x1, C2 lambda 2 x2 plus C3 lambda 3 x3 equal to 0. So similarly, let me try and eliminate this third term, and I have now, so look at this, these two terms alone coming here, and therefore you can figure out that this is going to be C1 times lambda 1 minus lambda 3 x1 plus C2 lambda 2 minus lambda 3 x2 equal to 0. Now, can we stop here and say, use the same logic and then say that, this is a non-zero vector, that's a non-zero scalar, this is a non-zero vector, that's a non-zero scalar, and therefore can the combination can't be 0? No, we can't say at this point, because we have two terms here, and therefore it really doesn't prove that C1 and C2 equal to 0. So we'll have to proceed, and here is how we extend this concept into this inductive principle. So take the third equation and multiply that again by a. Right, so when I multiply that by a, look at what we get. I get C1 lambda 1 times lambda 1 minus lambda 3 times x1. Similarly here, only two terms, because anyway I did not have the third term here. Let me call this as the fourth equation. With this fourth equation, I can actually eliminate this term as well. That's the idea. So in the original two equations, I am eliminating the lambda 3, the third term. By proceeding with one more multiplication by a, I am able to remove now this second term as well. So let me use fourth equation and subtract from it the third equation, multiplying the third equation by lambda 2, right, because I have here lambda 2 extra, so these two I would want to cancel. Let's take a look at this. So equation 4 minus lambda 2 times equation 3 is going to give me C1 times lambda 1 minus lambda 3, right, so this is common, and we had multiplied here by lambda 2 and subtracted here, and therefore this would become lambda 1 minus lambda 2 times x1 equal to 0. Now look at this, right, so we know that lambda 1 is different from lambda 2, so this is non-zero, this is also non-zero, and I have a non-zero vector, right side is becoming 0 vector. How can that be possible? Because it is just a multiple of a single vector which is non-zero, and therefore we get the fact that C1 has got to go to 0. Similarly, we can obtain that C2 and C3 will also go to 0 with the similar logic that we can apply. That's it. With this idea, we will be able to prove with respect to n as well, and therefore this is the claim we have. We are going to say that the eigenvectors are linearly independent whenever we find that their eigenvalues, the corresponding eigenvalues, are distinct. Now we will take on the opposite statement. Does it mean that if I have same eigenvalues, will my eigenvectors be linearly dependent? The answer is no, and I am going to answer it with a simple counter example. This is the counter example. What about the identity square matrix n by n? It has got n eigenvalues. This is something we have already done. And all those eigenvalues are equal to 1, which means that the lambdas are repeating, alright. But how many eigenvectors can we have for that? Every single vector in Rn is going to be an eigenvector, which means that we can easily pick any n linearly independent eigenvectors. And therefore, that's the counter example to argue and say that when we have same eigenvalues, it need not mean that my eigenvectors have to be linearly dependent. Here we have repeating eigenvalues, but my eigenvectors are linearly independent. The more important fact is, when we try and substitute this repeating eigenvalue in the matrix A minus lambda I, we will have to look at what is the dimension of the null space. In the identity matrix, all that you have is only a diagonal. In A minus lambda I, it is only becoming 1 minus lambda. When I substitute for lambda equal to 1, all the n columns become zeros, which means my null space dimension is actually n. Therefore, I am able to pick up n independent eigenvectors. The same principle can be applied to other matrices as well. Alright. So, we will try and put this repeating eigenvalues in a formal term so that we can have some idea about repeating eigenvalues and non-repeating eigenvalues, and linearly independent eigenvectors and linearly dependent eigenvectors in a formal term. So, what we are going to look at is what is called as algebraic multiplicity and geometric multiplicity. We are not going to go very deep into this topic, but we must know what these terms mean, and therefore let me give you a brief idea. What is algebraic multiplicity of an eigenvalue? Remember, algebraic multiplicity is talking about an eigenvalue, right? And it's saying the number of times an eigenvalue repeats when it is a root of the characteristic polynomial. So, in the case of identity matrix, we are talking about lambda equal to 1. It's repeating how many times? N. Therefore, algebraic multiplicity of this eigenvalue 1 is n. What's geometric multiplicity? Again, is defined on the eigenvalue, right? Both of them defined on the eigenvalue. The number of linearly independent eigenvectors produced by the eigenvalue is said to be the geometric multiplicity of that eigenvalue. In the case of identity, what's the geometric multiplicity of this lambda 1? That is n, because it is able to produce n independent eigenvectors. But you can go back and check with the previous examples that we had done. There were examples where we had a single eigenvalue, and it was only able to a single eigenvalue which was repeating, and when we substituted that in a minus lambda I, we were only able to produce a single eigenvector, though the eigenvalue repeated twice. Then there were a few examples that way. So, the algebraic multiplicity there is 2, but the geometric multiplicity turns out to be 1. But we are not going to dwell too much on this topic. We are going to leave this aside here and proceed to now look at the facts that we have got till now. Initially, we started off with diagonalization, and we said if my square matrix has got n linearly independent eigenvectors, then I can diagonalize it. Okay. Then we looked at when are the eigenvectors linearly independent. We said if the lambdas are distinct, then my eigenvectors are definitely independent. Let us combine these two and make a strong fact, right, and also look at some associated facts with it. So, here are 4 very important results that we must keep in mind with respect to eigenvectors. Any matrix that has got distinct eigenvalues can be diagonalized. This is a simple combination of the two statements we have just made above, right? If I know my eigenvalues are distinct, that means that my eigenvectors are independent. If my eigenvectors are independent, I know that they can be diagonalized, right? That's it. So, that's the important fact which is stated as result 1. Result 2 is another interesting fact. It says that the diagonalizing matrix S need not be unique. Simple fact is that any multiple of an eigenvector is also an eigenvector. So, instead of keeping S to be the S has, remember what is S? S, the columns of S have got the eigenvectors from the matrix A. Now, instead of keeping those eigenvectors, instead of saying x1, x2, x3, I can keep say 2x1, 3x2, minus 4x3. All of them will remain to be eigenvectors, and therefore it means that we can still diagonalize the matrix by using another S. And therefore, the diagonalizing matrix S need not be unique. The third result: not all matrices have got n linearly independent eigenvectors, and hence not all of them are diagonalizable. Some odd result, something like saying, when we have a matrix, do we always have a solution for Ax equal to B? No. We may need to find for a square matrix, if the inverse exists, then we are going to talk about a single solution being existing. Similarly, on similar parlance, there are matrices where we can diagonalize them, and there are matrices where we can't diagonalize them. And here is the important criteria to figure out when is a matrix diagonalizable. It is diagonalizable when it has got n linearly independent eigenvectors. Now, we are not stating it as if a matrix has only distinct eigenvalues, then only it is diagonalizable. That's a wrong statement to make. Even with repeating eigenvalues, it is still possible, because I may be able to produce n linearly independent eigenvectors. Therefore, that fact must be kept in consideration. So, look at the third result very carefully. when do we say that a matrix is diagonalizable? When a matrix has got n linearly independent eigenvectors, then it is diagonalizable. If not, it may not be diagonalizable, or it is not diagonalizable, right? So let us move to the result 4. Are there any other matrices that can diagonalize a matrix A? In this case, we are looking at S, which is comprising of eigenvectors of A. Instead of that, can I pick some other odd matrix which will also diagonalize A? The answer to that question is no. There are no other matrices that can actually diagonalize A. Okay, so how can we understand that fact? So let us look at this. A times S is equal to S times lambda. Let's not worry about what is there in S. Let us take the first column of S, so to be some Y, right? The column is some Y. We are really not sure if that's an eigenvector or not. Okay, fine. So if for diagonalization we need this to be true. Okay, let's take a look only up at the first column of the product on the left hand side and the right hand side. The left hand side will give me A times Y. That will be the first column in this product, right? So that will be A times Y. Let's take a look at the first column on the right hand side. Remember that the first column again here is Y. We are not sure if it's eigenvector or not, but Y times lambda 1, right? So that's what I'm going to get in the product in the first column. So this is what I get. Now look at this. A times Y is equal to lambda 1 times Y, and what does that mean? It means that Y has got to be an eigenvector of A, right? So that tells us the summary of what we have done till now, and these 4 are very important results. Now that we have these results with us, let us try and do some examples. Let us try and do diagonalization of a matrix. So if this is my A, first we need to figure out my eigenvalues, and therefore we need A minus lambda I. We have this. Look at the determinant. Take the characteristic equation, solve for the roots, we have the eigenvalues. Use the eigenvalues, put that in A minus lambda I, find the eigenvectors being the null space vectors of A minus lambda I. We have the 2 eigenvectors. They are distinct here, and these must be linearly independent. That's a fact we have proved, and therefore now we can even verify that, right? Now let's talk about the matrix S. Remember, the matrix S has got the columns from eigenvectors of A, which means 3 minus 2 and 1 1. I have put them in a matrix. That's my S. Similarly, from here I can get my S inverse. I know it will exist because these two are linearly independent. So I figured out the S and S inverse. All that I need to check is does it really diagonalize? Let me try and do that. S inverse times AS. Does it give me the lambda? And what is lambda? Lambda, we said, must be having minus 3 and 2 on its diagonal. It must be a diagonal matrix. Is that really the case? Let's check. Right, so look at this multiplication. So I've done all the multiplication. Finally, the answer is coming out to be minus 3 2, which means that what we read in theory is getting practical now. It is definitely working. No surprises for that. Right, so let's do a few more applications and maybe even look at matrices that are singular and non-singular, whether they're diagonalizable, not diagonalizable, etc. So look at this interesting matrix, and let's first check if this is singular or not. So if I look at the determinant of it, definitely not equal to 0. So this is a non-singular matrix, right? So let's look at this eigenvectors. So let me first find the eigenvalues. So this is my A minus lambda I, and then I look at my the characteristic equation, and I find here that the lambda repeats, which means 3 is repeating twice, and algebraic multiplicity of that eigenvalue 3 is 2. Okay, so let me substitute 3 in this equation, and this is my matrix A minus lambda I. Now look at the null space dimension. That's clear, it is only 1, so this can produce only one eigenvector. Where's the second eigenvector? And therefore I can't have diagonalizability feature for it, and that's it. We are saying this is only one eigenvector, therefore it's not diagonalizable. I had a non-singular matrix, yet it is not diagonalizable, which means the feature or the property of diagonalizing does not depend on whether a matrix is singular or non-singular, but more dependent on the number of linearly independent eigenvectors that we can bring out for that matrix. Right? So this is what we are noting. A is not singular, yet it's not diagonalizable. Okay, let's take another look at let's take a look at another example, which is matrix which is singular now. So this is a singular matrix. We can figure out the determinant is 0 straight away. Okay, but anyway, let's figure out the eigenvalues. Okay, so we figure out the determinant of A minus lambda I, and we get the eigenvalues to be 0 and 2, non-repeating, the distinct, therefore the eigenvectors are going to be independent. So we are going to get two independent vectors, eigenvectors. Right? So let me substitute here and find the null space solution here. This is 1 minus 1 and 1 1. We have two eigenvectors for the matrix A, which is supposedly singular, and we can diagonalize it, right? So I have my S, I can find my S inverse, and you can actually verify if S times A times S inverse is giving us lambda or not. Please go ahead and verify. But what is the most important point here? We find that A is singular, yet it is diagonalizable, right? So let's not make any assumptions from here saying that non-singular is not diagonalizable and singular is diagonalizable. No, let me take you to another example. So here is another singular matrix. Let me find the eigenvalues. They are repeating. Very important statement we are making. They are repeating, and the algebraic multiplicity is 2. When I substitute for this lambda here, look at A minus lambda I. The null space dimension is 1. Therefore, I can produce only one eigenvector, which means the geometric multiplicity is 1. And what does that say? It's not diagonalizable. There is a singular matrix but not diagonalizable. Singular matrix diagonalizable. Previously, we have seen non-singular matrix diagonalizable, non-singular matrix not diagonalizable. Therefore, we must keep these two facts separate from each other. Singular versus diagonalizable are two very separate features, and let's not mix them at any point of time. Let's just summarize what we have learned till now. This is the important point. We know that invertibility or being non-singular depends on non-zero eigenvalues, or saying n pivots, whichever way we want we can put it. But definitely if you find an eigenvalue to be 0, you know that that matrix is not going to be invertible. But diagonalizability depends on my n linearly independent eigenvectors and not whether my lambda is 0 or not. If one of my lambda goes to 0, that's still fine for diagonalizability, but that's not fine for invertibility, right? So that's what we have learnt till now. Let me take you through one more example where this is something that we had done earlier. In this case, we were finding that the lambdas were not even real, and the eigenvectors were also complex, right? They were using complex numbers. There are no real eigenvectors, but still, let us see if it's diagonalizable or not. Right? So this is previously we did rotation by minus 90. I've just picked up rotation by 90 this time. Similarly, find the determinant of A minus lambda I. We find that lambda is going to be I and minus I. Look at their null spaces, and I am able to figure out I got two linearly independent eigenvectors, I1 and minus I1. All right. Let's put that in S matrix, find the S inverse, and let's check what happens to S inverse times AS. Right, look at this here. S inverse times AS is bringing me my lambda back. That is the biggest advantage. Even when we are having no real eigenvectors, with the help of complex numbers, eigenvectors are still helping us in diagonalizing a matrix and giving us back this lambda. But the more important question is, why are we diagonalizing? Right? What is the big benefit of diagonalizing? That's the next question that we will look at. Let us say that I have some matrix A, and this is the same matrix that we have on top, right? This is the same rotation by 90 degrees. Suppose for some reason we need to find powers of this matrix, like A square, A cube, A power 4, etc. Okay, we can figure it out this way by keeping on multiplying matrices. Right, that's one technique. But can that be a better technique? What if we are given a more complex matrix and a larger matrix, and if you are asked raise A to the power 100 or say raise A to the power 1000, I mean how are we going to keep computing this, right? So that's going to become a little tough. All right, so let's keep this fact in mind, that can diagonalizing help us in raising a matrix to some power? A side effect of this is a simple idea to look at what could be the eigenvalues of a power of a matrix, and here is the simple answer to that. When I have lambda to be an eigenvalue of A, then I know that A times an eigenvector x will give me lambda times x. So let me pre-multiply on both sides by A. I am going to get A square x is going to become lambda times ax. I'm just taking the a inside, and I know that lambda ax is nothing but lambda x, and which means that this is going to become lambda square x. Now look at this equation here. A square is a matrix times some vector is giving me a scalar times a vector. That means that x has got to be an eigenvector of a square as well, and lambda square becomes the eigenvalue of a square. Right? So this is a wrong statement here. So lambda square is an eigenvalue of a square, and x is an eigenvector of a square. Now from here you can actually imagine what will be the eigenvectors of a cube or a power n. I think all the eigenvectors are shared from a to a power n. There is no problem there. And what will be the eigenvalues, right? So we can easily figure out what will be the eigenvalues of any a power n. So it is all going to be lambda power n, right? Okay, but with this was just a side product of what we were learning. More important is how is the diagonalization going to help us in raising a matrix to some power. And here is the most beautiful fact and one of the most important applications of eigenvectors. We know this equation. Let us try and multiply this again by itself, right? So multiply this, both the right hand side becomes lambda square. Look at this, when we expand out the associative principle here, these two get cancelled. I get s inverse times a square, s equal to lambda square. Just continue this and you will figure out that s inverse times a power k, yes, is going to become lambda power k. And from here, what is very interesting is this is a diagonal matrix. Raising a diagonal matrix to any power is the simplest thing that we can do. So if lambda is simply a 2 by 2 with a and b on its diagonal, lambda power k is going to be a power k and b power k. And what does that tell us? From this equation, I can get a power k to be pre-multiplying and post-multiplying on both sides. We get a power k is going to be s into lambda power k times s inverse. This is the huge benefit of using eigenvectors. If I have my eigenvectors s and s inverse and my eigenvalues, raising a matrix to its power becomes a simple multiplication of three matrices and not multiplying a matrix k times with itself. What a tremendous saving in computation. That is why eigenvectors are extremely powerful, right? So let me take the same example as a above and try and calculate something that we had done earlier by normal multiplication. Now let me use this new fact and see whether the result is same or not. For this we have already figured out the eigenvectors, so I have my s and s inverse. Here is my lambda. Let me substitute that here for a power 4 and see what happens. Right, so let me multiply all this and I am able to figure out that this is the same matrix that we calculated above, right? So a power 4 is coming out to be identity here. Take a look at the previous one here. That is again identity, right? So you may look at this example and say this is quite simple and what's the big benefit? What if we are really asked for a power 100? Let me take another example. This is another example which we had done previously. I have the eigenvectors for it. I have figured out the inverse as well. This is there in the same session a little ahead. We had done this, and the lambda. Let me multiply for a power 100. Look at this, right? So trying to imagine a power 100 with respect to this, I think we will probably need a computer. But look at this, right? So it is pretty easy for me to even algebraically, even though I may not know the number minus 3 power 100, that's fine, but I can write it out quickly in algebraic terms just by looking at this computation. That's extremely powerful when we are going to use eigenvectors for raising a matrix to its power. Now we see the real power of diagonalization. Okay, from here on in this session we will just continue. We are not going to continue the diagonalization, but we are going to look at some simple facts about eigenvectors of a product of two different matrices, and that may come in very handy later, and that is why we are trying to look at that fact. So let's say that we are given the eigenvalues of a and b, and we are interested to know what are the eigenvalues of ab. Right? We are interested to know the eigenvalues of ab. Suppose we are given eigenvalues of a and b. Here is a very interesting fact. If lambda is an eigenvalue of a and mu is an eigenvalue of b, can we write this way? Right? So if I have ab times x, I know that b times x will give me mu x. Right? We know that x is an eigenvector. Assuming that x is an eigenvector of b. Right? Assuming that x is an eigenvector of b, this gives me a times mu x. So I take the mu out and this gives me Ax, and we know that Ax will give me lambda x, and we got this, right? So it's saying AB times x is giving me mu lambda times x, and can we infer from here that x is an eigenvector of AB as well, and that the product of the eigenvalues of A and B become the eigenvalues of AB? No, absolutely wrong. It is a very wrong step that we have involved here without our knowledge, right? So let's take a look at this a little carefully. We said here, let x be an eigenvector of B. That gives me B times x is equal to mu x. Now mu times Ax, and we should have stopped the equation here. Who said that x is an eigenvector of A? We simply have been looking at Ax equal to lambda x, so we assume that and we said Ax equal to lambda x. No, x is an eigenvector of B. We never know whether x is an eigenvector of A. We just have to stop here. Therefore, using this way does not make sense, and therefore we can't conclude anything from this wrong interpretation. Alright, so that's the reasoning we have written down here as well, but definitely till this point it was right? So till this point let's go ahead, right? So till this point let's go ahead and then ask the question, what else can we infer? So all that we can infer from this point is that if x happens to be an eigenvector of A, then we can say that this would become u lambda x, and therefore x also becomes an eigenvector of AB. So the idea that we can say, all that we can infer from here is that if A and B share an eigenvector, then that also becomes an eigenvector of AB. Nothing more and nothing less than that. Okay, what about A plus B times an eigenvector? What about eigenvectors of A plus B? So let's try and take a look at this. We are saying that A plus B times x is going to be Ax plus Bx. So can I write it as lambda x plus mu x? Again the same mistake that we can do. We are assuming that x is an eigenvector of both A and B, which need not be the case, right? And therefore again let's state this principle very carefully. If x is an eigenvector of both A and B, then it remains an eigenvector of A plus B as well, and the corresponding eigenvalue also becomes the sum of those corresponding eigenvalues for A and B. Alright, so that's what we have with respect to AB and A plus B. Now, is there something more that we can really prove? Right, that's a very important proof that we are looking at here. We are saying that diagonalizable matrices, the moment I say diagonalizable, you must understand that each of them have n linearly independent eigenvectors. The diagonalizable matrices share the same eigenvectors if and only if they commute on their product. Now, it looks a little strange that a commutative product is able to give us a fact that they share the same eigenvectors. Let's take a look at the proof. Suppose we say A and B have the same eigenvectors, right? So there's one way we are proving. So we could assume that they have the same eigenvectors, they are diagonalizable. Then we will prove that they commute with their product. Let's try that first and then try and do the reverse, right? Let me assume they have commutative, the product is commutative, and then go back and say that they will share the same eigenvectors. Alright. If A and B are having the same eigenvectors, remember they are also diagonalizable, then I can write AB as S lambda 1 S inverse, again S lambda 2 S inverse. I have not assumed the same eigenvalues, but we said they share same eigenvectors, and therefore it's fair enough to say that these all will be just S and S inverses together. Now that gives me, what do I get? So I'm going to get S times lambda 1 lambda 2 times S inverse. Let me look at BA in the same parlance, and then I get the same expression here, S times S inverse, but only thing that is reversed is lambda 1 lambda 2, and here it is lambda 2 lambda 1, but they are diagonal matrices, right? And therefore in a diagonal matrix, you can take a look at this, this will come out to be the same. Why? Because all the diagonal terms of these products will just be, the square, not the square, I'm sorry, they'll be the product of those individual eigenvalues of A and B in the corresponding positions. And therefore, since this is the same, what we have is that the AB must be equal to BA, or the product is commutative. Let me try and prove this in the reverse direction. What if we have AB equal to BA and let's try and see whether A and B share the same eigenvectors or not. Suppose we assume x to be an eigenvector of A, then look at this continuing equation. AB times x is going to be BA times x. Look at the fact that what we have assumed we are using here in this important part, and therefore AX is going to be lambda x, because we said x is an eigenvector of A. Right? We don't know if it's an eigenvector of B. We have to prove that it's an eigenvector of B. Alright. Okay. So this will become lambda times Bx. Okay. Now take a look at this. A Bx is equal to lambda Bx. What we have is, let me just put a parenthesis around here, and this looks like A times Bx is giving me lambda times Bx. What does this convey? If Bx has to be some vector, because this is a matrix times vector, it has got to be some other vector, and I get that the resulting product is continuing in the same span as Bx vector, and therefore Bx has got to be an eigenvector of A for the same lambda. Okay, let me assume that A has got n distinct eigenvalues. If A has got n distinct eigenvalues, then its eigenvectors will be linearly independent. Now, when we say that each one is linearly independent, you can look at the span of those independent eigenvectors. They will all be simply lines or one-dimensional eigenspace. What I mean by eigenspace is simply the span of each of the eigenvectors. Since I have n linearly independent eigenvectors, each of them will be one-dimensional. Now, take a look at this. Bx is an eigenvector for the same lambda, which means the corresponding eigenvector x that we had got and this one probably must be in the same eigenspace. Why am I saying that? That's because all the eigenspaces are one dimensional. They are one dimensional. The direction really does not change. It is in the direction of x or in the opposite direction, nothing more or less, right? And therefore, it tells me that Bx has got to be an eigenvector for the same lambda, which means it must be in the same eigenspace as x, and x is one dimensional, and therefore all that in one dimension you can have is that Bx has got to be a multiple of x. And what does that tell us? That x has got to be an eigenvector of B. That's it, right? We are able to prove that assuming x is eigenvector of A. We started off with that, and we are able to prove now that x is an eigenvector of B as well. But we made a very strong assumption here, saying that let me assume that there are n distinct eigenvalues, which means that it may pick up linearly independent eigenvectors. But even if that is not the case, right, even when we don't have n linearly independent vectors, even if we have repeating eigenvalues or what, then I'm sorry, that was a wrong statement to make. I should have said even when we don't have n distinct eigenvalues, still if we are able to have eigenvectors, n eigenvectors that are linearly independent, we can prove the same fact as well. But that proof may involve algebraic and geometric multiplicities and eigenspaces, and we are not going to dwell too much into that topic, and therefore that part of the proof we are going to call currently out of scope, or not in relation with respect to the amount of linear algebra that we are looking at, and therefore we are going to exclude that part of the proof. But what we are stating here is that even when they are not distinct, the same result can be proved, right? And therefore it's a very important statement we have here. When do they share? When are two matrices sharing their eigenvectors? They share the same eigenvectors if their products are commutative. Alright, so in this session, let me summarize what we have learnt. We started off by asking the question, why diagonalize? Then we looked at 4 important results with respect to diagonalization, and we also saw examples where we had marked difference between diagonalization versus being singular or non-singular, and we have also looked at what is the use of diagonalization, raising a matrix to its nth power, and how simple or how easy to compute with eigenvectors. And finally, a few important facts about eigenvectors of A and B versus AB, A plus B, and when do they share eigenvectors? Let us close this session with a prayer. Om Shanti Shanti Shanti.